Hi, I'm Sid. I, along with Xiang, will be talking about a few of the features that went in Pinot 0.3, and along with that, how Pinot can be deployed on Kubernetes and Presto Pinot integration. All right, so let's take a few examples on query processing in Pinot. Let's say you have a column named first name, and you want to do exact match on this column. You want to count the number of rows where the first name is John. So let's see what the execution engine does to process this query. We'll first look up the dictionary of the column first name. We'll do a binary search on this dictionary to find the fixed with the dictionary ID corresponding to John. That happens to be 2. Then using that dictionary ID, we'll scan the forward index for this column to count all the number of matching records that match the dictionary ID. Since there is no index on the first name column, we'll have to scan the entire forward index for each segment of Pinot table. Okay, so now how can we make it more efficient? Let's say there was an inverted index on first name column. So the first step of query processing remains the same. You binary search the dictionary for the predicate value John, you get the dictionary ID. Then instead of scanning the forward index, we look up the inverted index using that dictionary ID to get a bitmap of all the doc IDs corresponding to that dictionary ID. And then you use those doc IDs to count the number of records that you have where matching with the predicate John. So this is much better than unlike the previous approach where we were scanning the entire table. Now, what if we are not doing an exact match? We want to do a regular expression match and an arbitrary match. So today in Pinot, we have an inbuilt function called as regexp-like, which allows you to do a regular expression searches on the columns. Now, in this particular case, what the user is interested in doing, counting the number of all rows where the first name has a prefix John. So it's a prefix query. So because this is a non-exact match, we cannot use the inverted index on this column. So what we will do is that we'll scan the dictionary from and that the size of the dictionary is the cardinality of the column. So we'll scan the dictionary and get the raw value corresponding to each dictionary ID. Once we get the raw value, then we do pattern matching with the regex that the user specified in the regexp-like function. And in this step, we compute a set of matching dictionary IDs. Once we have this set, we scan the entire forward index and count the number of records which have the dictionary ID part of the matching set. So the good news is that we are using the dictionary based matching, but still we are doing an entire full table scan to do a regular expression search. So how can we make this more efficient? Basically, what is missing in regular expression searches is the presence of a text index. As we just saw, that Pinot supports efficient query processing on primitive columns through a combination of dictionary encoding and inverted index. But for arbitrary text searches, we need 2 things. First, we need more than like regular expression search or phrase search. We also need fuzzy search, which is like an edit distance search. Today, the current support in Pinot, which is regexp-like, it does phrase searches, regex searches. It doesn't do fuzzy searches. And as we just saw, it uses a full table scan instead of an index, so it is not efficient. So in the latest release of Pinot, we added support for text indexes to do efficient regular expression searches on string columns, where like each column value is generally like a blob of heterogeneous text. To use the text index, you need to use a new inbuilt function called as text match, where the first argument could be the column name on which text you have created text index, and the second argument is the search expression. Now, how does this compare with the regexp-like, which does not use an index? We took a data set of 500 million rows and a text corpus of size 200 GB, and we ran 2 random queries with reasonably high selectivity. In one query, we just searched for the phrase, regex search for phrase United States. The selectivity is 150 million. Now, with text match, this query completes in 2 seconds. And with the regular expression search regexp-like, it takes around 9 minutes. The second query, a much lower selectivity, around 20 million. It takes around 500 milliseconds for text match and way more with regexp-like. So as we can see, the arbitrary text searches are way faster with text indexes as compared to regexp-like. All right, so now that we have support for text indexes in Pinot, let's see how we can use that to do some log analysis. Let's take an example of a query log and a resume file. We store the query log and the resume text in 2 string columns in a Pinot table. We create a text index on each of these columns. And then we can do a number of different kinds of queries using the text index. For example, you may want to count the number of queries, which count the number of group by queries, which are using a between filter on time column. Or you may want to find the number of candidates that have like machine learning and GPU processing in their resume skills. Similarly, you may want to find the candidates that must have distributed systems and either Java or C++ in their resume text. So these are just few of the examples of the kind of text analysis that you can do using text match inbuilt function. All right, so let's talk about a few design details of text indexes. Pinot uses Apache Lucene for the underlying to create the text indexes. Apache Lucene is basically a search engine like library to do arbitrary text searches efficiently. The centerpiece data structure in Lucene is an inverted index, which basically maps words or terms to the corresponding doc IDs. Document or row is the unit of indexing in Lucene. Just like other storage and columnar data structures in Pinot, we also create text indexes on a per column level during segment generation. So per column, per segment level, we create text indexes. During segment generation, we take the raw column value on which the text index is enabled on, and we create a Lucene document out of it comprising of 2 fields. One is the text field, which has the textual value, which is supposed to be indexed. And then there is a stored field, which is basically just stored inside Lucene. We don't index it. It is basically a monotonically increasing ID to map each document that we add to Lucene index back to its Pinot doc ID. Also, the raw value that we store inside Lucene for indexing, it is not physically stored because we already have it in our forward index inside Pinot. The text index is made part of the Pinot table segment and directory structure. This would be the directory for the current V3 segment format. So under your table directory and then the segment directory, you'll have an index directory for Lucene text index. Let's take an example of how the query processing will happen on text index. On the left-hand side, there is an offline data ingestion job that basically builds an offline segment. As part of the segment generation, we would create text indexes on as many columns as the index is enabled on. And then once the segment is fully built, the segment is written to the segment store. On the server side, the server loads the segment. It basically memory maps the segment. As part of doing that, we also load the text index. It is also memory mapped. The entire text index directory is memory mapped. And we create a text index reader during segment load to use later during search query processing. Now here, the query processing using text search is more or less similar to how the filter processing works today in Pinot. We create a text filter operator, which basically executes the where clause of text match. It passes on the search expression to the text index reader. Reader compiles that search expression, and then the end result is a set of matching doc IDs for that search expression. And then based on whatever you have in the rest of your query, whether it's and on another text match filter or something else, we basically do the same thing. We merge the doc IDs or intersect them, whatever. So in this case, there are 2 predicates on the text match columns, and we just AND the set of doc IDs after the result is retrieved from Lucene text indexes. So one of the key optimizations that we had done during the implementation of this feature was around the doc ID translation. So Lucene index is basically composed of multiple sub-indexes. Based on how the documents are added to the index and at what boundary they are flushed from memory, it creates multiple sub-indexes. Each sub-index is basically a fully self-contained piece of index capable of serving the search queries. So the Lucene index writer will buffer documents up to certain memory threshold. Once a certain memory threshold is hit, it will flush them onto disk, and that will create a Lucene sub-index. The key thing over here is that the doc IDs, as and when the documents are added to Lucene, Lucene also assigns a monotonically increasing doc ID to each document added. But these doc IDs are relative to each sub-index. Now, this does not work well for Pinot because Pinot's filter processing engine is based on retrieving a set of doc IDs for a given filter and then either merging them or intersecting them or doing a union of them with other set of doc IDs. Since now there is no one-to-one mapping between the Pinot doc IDs for the entire table to the corresponding leucine doc IDs, it breaks our processing. So what we were doing is that as part of the document that was added to leucine, we stored another field, which was the Pinot doc ID. So now this makes our search query processing in two phases. When the search query is executed on leucine, it returns a bitmap of matching leucine doc IDs. When we then iterate over each of that the leucine doc ID and then get the corresponding full document from leucine. And then retrieve the Pinot doc ID out of this leucine document and then store the Pinot doc ID in a bitmap and find it. This is the result of executing text search filter in Pinot. In our performance testing, we found out that this particular operation of constructing an entire physical document for each matching doc ID was becoming a major bottleneck for throughput testing. It was consuming a lot of CPU and thus our queries were not scaling well with the increase in QPS. So the solution was, firstly, we merged all the leucine subindexes into one index, and we do this at the segment completion. Secondly, when the Pinot table segment is loaded in memory, as part of that, we iterate over the leucine index once, and for each doc ID, because now we have merged all the subindexes into one index, now there is one-to-one mapping. Like, so if you have like 1,000 rows in your segment, you will have leucine doc IDs between 0 and 999. So we'll go over all the doc IDs and then retrieve the Pinot doc ID and store this pre-built mapping in a file and then memory map it during segment generation. During loading the segment. And this file is then later used during query processing so that we don't have to retrieve the entire document out of the leucine. This particular optimization gave us 40x to 50x performance improvement for our throughput testing. So as you can see, we now get better scalability with increase in QPS. The graph shows results from some testing that we did from 1 QPS to 20 QPS, and the latency kind of stays more or less the same as the QPS is increased. Okay, so now so now referring to a diagram that Kishore had presented earlier, the whole the way we fit text index and the query processing or text index into Pinot was easy because of the modular architecture of Pinot. We have the columnar storage structures and indexes at a per segment level. So that's on the storage side and storage and indexing side. Secondly, on the query processing side, we build a physical plan for execution at a per segment level, and each server executes the physical plan on a set of segments, and then we combine the results. So now this whole architecture of planning, of storage, indexing, planning, and execution allowed us to create a new index as part of the Pinot ecosystem very easily. So it basically goes to prove that tomorrow, if you want to add a couple of more indexes, you just have you don't have to like do surgery of a lot of parts of Pinot. You can just make small amounts of changes inside the execution layer of Pinot. All right, so moving on to SQL support on Pinot. Currently, Pinot supports PQL, which is like the Pinot query language. Although it is SQL-like, it has some difference in syntax from SQL, and semantically it is quite different because it does not return the response in table format. So what we did in order to engage wider audience that like SQL and other systems which support SQL, we moved to Apache Calcite. So our query parsing and logical query planning is now done as part of Apache Calcite. The physical planning and the building the per segment level execution plan is still done inside Pinot. Using Calcite allows us to be able to support all the SQL syntax, although we still don't support the other SQL operations that are not supported in PQL, like joins and like subqueries or inner queries. But other kinds of SQL syntax is supported. The main difference is that now the query response is tabular, so which allows easy integration with like data visualization tools, Superset, Grafana. So if you take an example of a group by query where we have like two aggregations, average and min, and then you're grouping by an age. In PQL, the response was not tabular because each aggregation was returned as its own result. So if you see the first result here is for the min aggregation function, and that is there along with its group by key, right? And then we have a next set of result, which is the average aggregation function, and then along with the same group by keys. So this is not tabular. In SQL world, the response is completely tabular. So you have a metadata, which is basically the schema comprising of the column data types and the names. And then it is basically an array of rows where each row is returned in a single piece together. And so you have all the column values side by side, as opposed to returning the results individually in the PQL format. Also in PQL format, each result, no matter what the data type of the column is, was returned as string. In SQL, it is returned as based on what it is. Like in this case, age is an integer, then the output of average is double, and the output of min is long. Also in SQL, you have much more flexibility on adding order by, either on the aggregation, on a subset of aggregation columns or group by columns. In PQL, by default, we were returning the results sorted descending on each of the aggregation function. In SQL, you can do like select and then group by age, order by either the average column, min column, or a combination of both, or the group by column. Another key thing that was introduced in Pinot 0.3 was new plugin architecture. So the main goal here was to simplify the dependency structure that a couple of modules had in Pinot. Over the last couple of years, due to rapid development and as the community, open source community grew, and we integrated with a lot more systems, the dependency structure became complex, especially with respect to different kinds of file formats that we support and external systems like AWS S3. So we needed to simplify this to support better pluggability and to basically make the developer contribution more productive in terms of if they want to add a new support for some external system or integrate with another system, then it should be fast and they should not get themselves into a complex dependency structure. So what we did here is we created a SPI, which is Pinot SPI as a service provider interface. So this is the main module which the Pinot core module now uses. As part of Pinot SPI, there is this module called Pinot plugins, which basically extends this. In Pinot plugins, we have grouped different kind of plugins based on what function do they provide to Pinot. Like for example, what is the input format of your data? So that is Pinot input format. It could be OR, Cavro, JSON, Parquet, etc. Then the file system, basically where is your data resident? It could be on Hadoop, or it could be Google Cloud or Azure or S3. Then are you doing a stream ingestion through Kafka, or are you doing a batch ingestion through Spark, Hadoop, or standalone? So this basically modularized the overall structure, static structure of Pinot, and simplified the dependency diagrams. So due to time constraints, I couldn't go over the real-time text indexing. There is a blog post that is coming out very soon in the next couple of days with a lot more details on design and implementation and many other optimizations that we did to get the functionality for text indexes. So stay tuned for that. I'll now let Xiang take over for the rest of the presentation.
Hello, this is Xiang. So I'm going to talk about how to deploy Pinot in Kubernetes. Basically, today's talk, I will cover how the deployment will look like, how you can get data into the Kubernetes Pinot, and how you can access the Kubernetes cluster, as well as some simple operations on top of that. And at last, if there's enough time, I will probably show some Presto Pinot integrations. And also, this section, I will try to do a live demo. So just be prepared if there's some awkward silence because I'm trying to do something. Okay, so let me present. Yeah, as nowadays, the container technologies are getting more and more adopted, and it has a good isolates of the applications from the host, so that we don't worry where we're going to deploy our containers. And in order to run and manage those containers, but naturally we need to get some tooling to automate the container deployment and the container scaling, and also how we can do the load balancing. So Kubernetes is built from Google, and now it's one of the most popular container orchestration tooling. And it manages a desired state defined by the user and help the user to scale out the application's deployment and also do the distribution for their traffics. And also Kubernetes works brilliantly with all cloud vendors. So you can run it in either public cloud or you can run it on the on-prem data center. So with all those benefits, the next question here is how we can actually leverage Kubernetes to deploy Pinot. So the goal here is that we can use Kubernetes to manage stateful services like Pinot, which requires a dedicated host name, and we can hosting the large amount of the data on disk. And meanwhile, we want to ensure that we can scale Pinot at each layers independently, like controller, broker, server. And also, there's no single point of failure, and as well as we want to have the auto recovery from the failures. So here is a very high-level Pinot deployment on Kubernetes. If you take a look at the middle part, we'll basically try out to use stateful set for all the Pinot component, as well as the zookeeper. So because the stateful set is a workload API object used to manage those stateful applications in Kubernetes. In terms of the container configs, it provides us very stable and unique network identifiers, as well as stable and persistent storage. So in terms of the deployment, it provides ordered and graceful deployment, as well as scaling, and also we can do the automated rolling updates. So if you see here on the middle part, we have Pinot zookeeper as a stable set, and then we have a Pinot controller, Pinot broker, and Pinot server, all connecting to it. And also controller and the server will be able to pull data from like deep store, as well as like streaming data sources. Meanwhile, we will expose Pinot controller and Pinot broker through the load balancer. And the Pinot controller will be exposed to the system admin usage, as well as the web console for like ad hoc data exploration. Pinot broker will be used majorly for the data applications and as well as the dashboarding use cases. So before I'm going to the detail, I will try to ramp up my script. So basically here I will try to use Helm chart as to basically help me to do the deployment. I try to make this as like as simple as the one command to deploy Pinot. However, here I need to run 3. So below are the 3 commands I'm going to use. And yeah, just to show I'm not cheating, this is my Kubernetes namespace, and it's empty. And I'll run this 3 command. It will try to deploy Pinot. And just in case we're like getting the current status, everything is trying to start itself. And okay, let's go back to the slides. So basically, this command will try to install Pinot with 1 controller, 1 broker, and 2 servers. This is just for simplicity of my demo. And the Helm chart is a tooling to do those kind of packaging, templating, and operations for the Kubernetes, as we have multiple components, like multiple stateful sets we need to deploy in Kubernetes. So this is the ideal state or the desired state it will look like after the deployment. Just in case my demo doesn't succeed, this is something we should look for. So here is Pinot controller. So Pinot controller will leverage a stateful set to keep a constant host name. So basically from here, each Pinot controller based on their container and pod. So the pod name is called Pinot-controller-0, and the next one we will call Pinot controller 1. And hence, based on how many pod you are going to deploy, it will basically increase those numbers. From the network layer, we're going to have a headless service, which will manage the unique identities, so that within the namespace, all the other pod will be able to recognize Pinot controller 0 as the pod name and be able to talk to this node. And meanwhile, we will have the load balance service. It will actually expose the Pinot controller as the high-level service name. And this will be exposed to the external traffics and also as the load balance, so that the request of calling as Pinot controller will be redirected to either Pinot controller 0 or Pinot controller 1. And hence, if there's any more pods. So for the scaling factor here, usually we will have a cluster size, usually start with 3. This is for all the failover consideration. And typically you just need 3 nodes and no more than that. At least from our cluster management experience, it can sustain up to like 1,000 nodes. So typically no worry to change this number. For the deep store management, as Pinot controller has like this kind of deep storage support. So in this Kubernetes deployment, you can try to set up with either native Pinot file system plugin, so that you can use like S3 plugin or Google Cloud storage plugin. So that will actually connect Pinot controller to this cloud storage, and then you can directly use them. Another way is that you can actually mount a persistent volume, which supports the access mode as the read-write menu, as we need to actually mount the same persistent volume to all the Pinot controller nodes. So currently, there's only things like NFS or Assurefire or SafeFS that's very limited support for that. The third option is that we can leverage some Linux fuse lib. For example, you can use the Google Cloud Storage Fuse that will actually try to mount your Google Cloud bucket as like a file system path, which you can actually use. However, that plugin or this kind of library may not be super stable, so just use by your own risk. And typically for the instance type, if you try to deploy it on cloud, we typically try out those balanced CPU and memory setup. And this is, for example, we can use like EC2, those M5.2x large, which is like 8 cores, 32 GB RAM for this kind of setup. Okay, now let's come into the Pinot broker. It is a stable set to keep the constant host name also. And this is for like multi-tenancy mode. And for network, we will have the same headless services for internal communication and load balancer for the external traffics. Scaling factor here is majorly based on the query load. We typically start with 2 to 3 nodes, and based on the query load, you can actually add more workload, more part to that. For the instance types, typically we do balance the CPU and memory also, and this is how we can do like M5 X large and keep adding more instance. So for the Pinot servers, this is a little bit complicated as Steve was in terms of handling more data. So typically we use persistent volume. Always we recommend SSD as the persistent volume. So you can either do it with remote or with the local. So for the instance type, for example, if you try out those EC2 or like EC2 boxes, which doesn't support a local disk, you can always mount a very large EBS. It's like elastic blob storage. And if you have like a very large boxes, which actually have good SSD, you can just mount your host path to the node, which will be actually rewrite to the local instance. So now let's try out more with demo, and we want to see how the cluster looks like. So okay, now everything is running. So we are going to do first try out table creation. So here, I'm just going to run these two commands. It will basically try to create a table which is called COVID-19 Recover the Global. This is to see how the world is progressing in the current epidemic, which caused this virtual meetup. And basically in this job, we defined this is like a Pinot schema. And we have another thing called Pinot table config. And hence there's a Kubernetes job, which will basically call the table creation config, which will create the table. And then next thing here is we're going to load data into Pinot. So here, basically there's like a typical data ingestion workflow. You can try to do the streaming ingestion through Kafka or the batch ingestion through like the deep storage and with like the execution framework like Hadoop or Spark to process your data and then build pin segments and push. So here it's like a typical batch workflow. It's like what we do the ETL. So this is like the sample script I'm going to run in order to ingest this COVID-19 recovered global data. So the first thing I'm going to try is I'll try to download this the raw data from the John Hopkins dataset from GitHub, and then I will run a Python script to do kind of the data transform. And then I will try to run the Pinot ingestion job, which will actually create a Pinot segment and then do the push. So this is how the ingestion job looks like. And let me try to run it. Yeah, so this job is running. And we should be able to see the data very soon. And by accessing Pinot, we basically have like query endpoint and as well as the admin APIs. So for the query entry point, if you click on here, it will just show some sample data. Basically, this is all the COVID-19 recovered data by the date and by the countries. We can try some like simple queries. For example, here we want to run this query to see what kind of the top countries which have the total recovered people. And meanwhile, we are able to query Pinot from their work endpoint. So it's like you can do a curl query to get the results. So another thing here is about the admin APIs. Basically, you can go to here. It's like a Swagger UI, which you can access to access all the Pinot metadata and APIs. You can get like a schema, table config, or the segment assignments. So because of the time constraint, I'm going to only show this. This is about a Pinot table segment assignments. Basically, here we just uploaded 3 Pinot segments. If you see here that each segment is being distributed into 2 nodes. And now let's try to see how we can actually scale up Pinot. So we will first try out to use the Kubernetes command line, which will actually scale Pinot from 2 nodes to 3 nodes. So this will show that, okay, the Pinot server is being scaled. And if you see here, we will get 1 more Pinot server from here. And now, like next thing here is we'll try to see how we can do the workload rebalance. So this is the command I'm going to run. Basically, it will actually rebalance the Pinot table. So once this command is finished, we can actually call it again. This is to get the Pinot external view. If you see here that the old assignment shows that the server of the segment are assigned to only Pinot server 0 and 1. Now, these 3 segments are actually being evenly distributed through all the 3 Pinot nodes. So, yeah, so that's pretty much it for the simple operations. And the last part, I will just show some integrations with all the hard work that Uber folks have been done for the Presto. So here, I'll just try a very simple Presto coordinator YAML file. We just apply it. It will try to deploy the Presto with the Pinot connector built in. And the next thing here is that I'm going to run a Presto CLI client. This client will actually connect to Presto, and we can run some simple Presto queries. For example, this will show the table, and we will see the table just created in Pinot is also showing up here. And here we can describe the table with the configurations. And here we just want to show some simple select star queries. And here we can run some, I mean, this is just the same query as I run in the Pinot query console for the top recovered countries. And here we can run some like even more complicated, like the subqueries or the drawings. This will basically try to run this top recovered country for 2 dates and try to join these 2 results. It's just some not too meaningful queries, but it shows the great capability of Pinot with Presto. And that's pretty much it.